This is problem 16.29. It's on page 1143. The 100 millimeter radius brake drum is attached to a flywheel that is not shown. The drum and flywheel together have a mass of 300 kilograms and a radius of gyration of 600 millimeters. The coefficient of kinetic friction between the brake band and the drum is 30%. Knowing that a force P of magnitude 50 newtons is applied at A when the angular velocity is 180 RPM counterclockwise, determine the time required to stop the flywheel when A equals 200 millimeters, B equals 160 millimeters. And those are dimensions that I don't know why they didn't just put them on the diagram, but there we have it. Okay, at first I looked at this and I thought, well, they didn't tell us where the strap is attached at B. They didn't give us the dimension, but if you think about it, the diameter of the drum constrains it. So, for example, the drum is here. There's a band that goes around it. It's just a band brake, which is actuated by a lever where force P of 50 Newton, I thought it was 75, I guess it's 50 Newton magnitude is pulling down. There's a pivot, C, not in the center, but somewhere over here, offset from the center of rotation of this drum. And then point B is the connection point, as well as D for the brake. Okay, it looks like O, but that should be D. They did call this central pivot O, and that's fine. We use that as the origin. And then this point is a ground pivot called C. So anyway, you just pull down on the lever, and what does that do? Well, that tries to make this point move up farther than this moves down, so the brake tightens up on the drum and causes it, along with the flywheel, to slow down. The friction coefficient mu was given as 30%. The radius of the drum was 0.1 meters. I don't remember if that's in the problem statement. I think it is, or the diagram. The mass of the drum and flywheel together is 300 kilograms. And the radius of gyration, I'm going to label that R sub G, which is the square root of the inertia moment over the mass, is 0.6 meters. So basically, I wanted to rearrange this and say I is RG squared times M, just in case you're not familiar with radius of gyration. Anyway, the initial angular speed of the drum is 180 RPM, and that is counterclockwise. Now, that's, if you convert it with to radians per second, that's 6 pi radians per second, and it's counterclockwise. So the drum is rotating like this. At least initially. Once we apply the brake, it's going to slow down. Now, we're supposed to find the time so that the final speed is 0. So apply the brake. You know, how long does it take to apply 50 newtons of force for this drum and flywheel to lose all of its energy? I started off realizing, well, I know there's a relationship between the tension at D and the tension at B, so I wanted to relate those two, so I simply said the tension at B over the tension at D, understanding because, you know, friction's acting this way on the belt, so that means if the drum's rotating this way, friction's acting, you know, along the entire belt length. Well, then that means the tension at B is more than the tension at D. And so from our study in friction, we know that this is E mu to the beta, where beta is the wrap angle. Okay, and so this is E to the 0.3 pi, because notice that the wrap angle beta is just 180 degrees, or pi radians. So basically this tells us that TB is TD times E to the 0.3 pi. Okay. So at least we don't have to do with both TD and TD. We've got an expression to relate the two. If we saw moments on the flywheel about O, well, let's see. If you think about it, we could take the belt and include it with the flywheel, couldn't we? Where we have tension at B and tension at D, right? And so if we saw moments about O, which is in the center of the flywheel, then we get TD times R, right? Because that's causing a counterclockwise moment, minus TB times R equals what? Well, I alpha. But the radius of gyration is what we know, so we'll substitute in the radius of gyration squared times the mass times alpha. Okay? We can rearrange this in order to solve for the angular acceleration. We just divide the whole thing by this. Now notice this radius is the radius of the drum. whereas this radius is the radius of gyration. It has to do with how the mass is laid out about the pivot point, the center of the drum and flywheel. And notice we can factor out an r, so I just wrote TD minus TB times r divided by rg squared times the mass in the denominator. Okay? I call this equation 1 because we don't yet have enough information to plug in here. For that, we'll have to take a free body diagram. So this is for the wheel. We'll have to take a free body diagram of the lever. The lever has tension at D acting downward, tension at B acting downward, and force P acting downward, with force at C acting upward. Now, I'm not really interested in the force at C, so I'm going to choose to sum moments on the lever about point C, taking counterclockwise as positive. In that case, we would have P times A, because the dimension here was called A. I know we know the number, but let me use symbols for the time being. The dimension between C and D was called B. So, summing moments about C, we've got A, and then to get the moment of TB, obviously TB causes a positive moment, but what is its moment arm? Well, the distance from C to B would be A almost, right? Really it would be, well, not A, actually, I'm sorry. It would be the diameter of the wheel, because that's the distance between T and B, minus B. I'm sorry, the diameter is the distance between B and D, and we have to subtract off little b, the dimension. So the way I did that was I said, well, give me 2 times the radius of the drum, because that's what I know, and subtract off b, and that'll be the moment arm for the force at D. And then finally, let me break the line, TD causes a negative moment, so minus TD times what? Well, that's just times B, right? Because we're summing moments about C. Must be equal to, well, notice that this is not moving, right? So this is just a static lever. So the sum of the moments equals 0. Now, if we rearrange things just a wee bit, or better yet, we can substitute in. So, let me think. Yes. P times A can be put on the left-hand side, and on the right-hand side, we would have B times TD plus TB, but I don't want to work with TB, so let me put the moment arm first, 2R minus B times TB, but TB can be written in terms of TD. So TD e to the 0.3 pi. Okay? And so now from this we can solve for TD, because notice TD is a common factor now. It would simply be P times A divided by the sum of the multipliers on TD. So B plus 2R minus B times e to the 0.3 pi. Okay. Of course, we know what these dimensions are. For example, P is 50 newtons, that's the force. A, they told us, was 200 millimeters or 0.2 meters. B, they told us, was 0.16 meters or 160 millimeters. Add to that 2R, well, the radius R is 0.1 meters, so that's 0.2 meters when we multiply by 2. Minus B, B is still 0.16 meters, and we need to multiply this last term by e to the 0.3 pi. Anyway, from this we can get TD. And so what happened was I got that TD must be about 174.38 newtons. And now if I plug in, instead of TB here, if I plug in TD e to the 0.3 pi, because I really don't care about TB. I mean, we could calculate it and see if the strap's going to break, but I'm assuming that's not going to happen. Now you notice we can just factor out TD. Right, 1 minus e to the 0.3 pi. Of course, e to the 0.3 pi is greater than 1, so we get a negative number, but that's okay, because the acceleration you would expect to be negative, right? If we're rotating this way and it's slowing down, then the acceleration is in the negative direction. I guess technically I should set up an XY coordinate system, but it's the typical thing we would use. Okay? So plugging in TD, 174.38 newtons times 1 minus e to the 0.3 pi. all over the radius of gyration squared, which is 0.6 meters quantity squared, times the mass, which is 300 kilograms. Well, let's think about the units for just a moment. In fact, I need some space, so let me get rid of this bit. If we think about the units for a moment, what do we have? Well, let's see, a Newton is a kilogram meter per second squared. That's all that's in the numerator. And then there's meters squared kilograms in the denominator. So we get rid of kilograms. And I feel like I'm missing a dimension somewhere. Did I mess up? Oh, yes, I did mess up. Let's see. Where did I go wrong? I forgot something. When I solved for this, I should have had an R out here. So let me correct myself. There should be an R. See, there's a common factor of R. I had TD minus TB. So I need to multiply by R here. So we have to add on 0.1 meters, the radius. I just forgot it in my equation. Anyway, so notice the units saved me. So there's an extra meter in the numerator, and so the meters squared cancel. We get 1 over second squared, which would be 1 over, well, radians per second squared, which is what we expect. So alpha is negative 0.2529 radians per second squared. And there's the angular acceleration. Well, that's a constant, right? Because the force P is constant, TB, TD are constant, and so the wheel slows down, the wheel and flywheel slow down at a constant rate. So from kinematics, we'd have that the angular speed final, which is 0, equals the initial angular speed plus alpha t. Therefore, the amount of time required for it to slow down is negative omega naught alpha, or divided by alpha. The initial speed, as I said, it's in the negative direction. Actually, it's positive. Oh, but I need the negative of it. The negative sign came from the equation. So negative 6 pi radians per second divided by the angular acceleration, which is negative itself, 0.2592, or 2529 radians per second squared. Obviously, the radians go away for free, and 1 of the seconds go away, so we just get seconds out of this. And I got a time of about 74.53 seconds for how long it takes. So it takes over a minute, even with 50 newtons of force, for this wheel to slow down because it has a decent radius of gyration and a decent mass. So it has a fairly large moment of inertia.